Today we're talking about graphing y equals ax squared plus c. So what we're doing is building off of our last section where we had y equals ax squared without anything else being added, subtracted, or doing anything to it. Remember, the a in the front of our x squared tells us a couple of things. If it is a positive number, then it will be a parabola opening upwards. If the a is a negative, it is opening downwards. If the a is greater than 1, then that means we are going to see a vertical stretch, meaning it's going to be closed in tighter than the parent function, y equals x squared. And if it is between 0 and 1, then that means it's opening up wider, which makes it a vertical shrink. So here we are for example 1. So we have a function g of x is x squared minus 2. We do want to keep using the graph for a little bit so we can make sure we know how to come up with these answers. So we're just going to start by plugging in our table. And again, these numbers don't have to be -2, -1, 0, 1, and 2. We are going to start seeing it change. So you don't want to get in the complete habit of doing this, but for now, these numbers work. So if I do -2 squared minus 2, I would get 4 minus 2, which is 2. If I plug in the -1 and square it, and then subtract 2, that becomes 1 minus 2 is -1. If I plug in 0, and then subtract 2, 0 squared is 0, minus 2 is -2. If I plug in the 1 and square it, and then subtract 2, I also get a -1, which is important. We see this -1 y value now doubling and duplicating itself. And then lastly, when I plug in the 2 and I square it, I get 4. When I subtract 2, I get 2, which matches nicely with the other 2y value from the original one where we had -2 going in. So first, let's go ahead and graph that. Now notice, when I do my graph, we want to keep as much of a curve as we can so that when we're coming down, we're not doing a sharp V point. We're kind of curving around that vertex and then coming back up. Again, so we knew it should be opening upwards, which it is. We also can see that our vertex is not where it was in the last section. Notice this time we kind of came down until we hit -2, and then we started to go back up. So our vertex is not sitting at 0, 0 anymore. It is now down here. So when I go on to the next one, so to graph the parent function, the -2 goes in, and when I would square it, I get 4. When -1 goes in and square it, I get 1. When 0 goes in and I square it, I get 0. Still not there yet. When 1 goes in and I square it, I get 1. And when 2 goes in and I square it, I get the 4. And again, by seeing those y's doubling up and repeating themselves, that shows me that I have found the vertex and it's come back around. So again, remember what that graph looks like for our parent function. So there's our parent function. So the blue is our f of x, and the black would be the g of x. Now to compare these, this time we've got a couple of things that we need to kind of make sure we note. We always want to talk about the vertex. So what do we notice about the vertex? Okay, so this time the vertex has moved. It is definitely not where it was before. So all we have to do here is say the vertex has been translated down 2 units from f of x. So we're comparing things to the f of x. So the one we're graphing, is the g of x function. So the vertex is translated down 2 units. Axis of symmetry, it's the same. That hasn't changed. We are still working on, oh, that's terrible. We're working on the same axis of symmetry. So let me just erase this and try that again. The axis of symmetry is the same. And remember what that is that imaginary line that goes right through the middle. In this case, x equals 0. Now, in this case, again, they are both opening up. And the one last thing we might want to mention about them is that they do have, in this case, the same width. They both have that 1 in the front They are opening up at the same width. So on to the next one. The next example 2. Again, this time we're not going to make the table for the f of x equals x squared. Hopefully we're now okay with that. So what I will do is I'm going to put that one in there right now so we can see that. So there's my f of x parent function that we're going to be comparing this to. So when I look at this one, we have g of x equals 4x squared plus 1. So again, we're still just going to keep working on the same table of negative 2 going in times 4 plus 1. That's going to give me 4 times 4 is 16, plus 1 is 17. When I move on to the second one, negative 1 squared times 4 plus 1. Negative 1 squared is 1 times 4 is 4, plus 1 is 5. The next one, when I plug in a 0 and I square it and then multiply it by 4, I get 0, plus 1 is 1. When the 1 goes in, now I'm going to do 1 squared, which is 1, times 4 plus 1, which is 5. And then 2 squared is 4, times 4 is 16, plus 1 is 17. So I'm going to pause the video, just show you that graph, and you can just plot those points while we wait. So here is your g of x, or g function. I couldn't fit the 17 on there. Obviously, we probably should readjust the scale and make it fit, but I think we can understand the idea here. I'm plotting these points. Again, we're focusing on comparing to that parent function. So a couple of things. Vertex. This time our vertex is not down. It's been translated up. So we want to make sure we write translated up 1 unit. Axis of symmetry. Same, right? Axis symmetry is the same. We have x equals 0. That's still the imaginary line that cuts these in half to make that symmetrical distance from that point on both sides. We both are seeing up. And this time, what do we see about the g of x? The g of x opening, it opens more narrow. And has a vertical stretch. Okay, so a couple of things whenever we talk about comparing. We want to include that vertex. We want to include the axis of symmetry. We want to talk about how it's opening upwards or downwards. We also want to talk about that width. Is it more wide? Is it less wide? More narrow? Okay, example 3. So this next one a little bit trickier. There's a little bit more going on in here. To be honest, I'm more concerned that we understand examples 1 and 2. But what we're going to do is we're going to show a translation of function f of x and how it goes to the g of x. Now notice in the notation here, the g of x function is not 3x squared minus something. It is the f of x minus 7. So hopefully what we've noticed in this beginning part is that c at the end of the ax squared is telling us a vertical translation from our vertex. Tells us whether the vertex is more up or more down. So what we want to notice here is we want to focus on what are the values of the f of x and then just subtract 7 from all of them. Okay, so we're going to go through this one a little bit quicker than maybe some of the other ones. Hopefully you can follow along and we can see if it makes sense. If it doesn't make sense, it's not really the end of the world right now. We'll have plenty of time to catch up on that in a future course. All right, so let's make a table. We're going to plug in -4, -2, 0, 2, and 4. Okay, and what we're going to do is we're going to first figure out what does f of x look like. Okay, so f of x, we're going to run all those numbers through the first equation that we see right here. So part of the reason that we're picking an even number is because we're multiplying by the 1/2 in front. So I'm going to kind of more verbally say these, and hopefully these make sense. So if -4 goes into this equation, -4 squared is 16, times -1/2 is -8, plus 2 is -6. Ooh. -2 goes in, and I now have 4 times -1/2, which is -2, plus 2 is 0. If 0 goes in, I just get 2. If 2 goes in, I get 4 times a -1/2, which is -2, plus 2 is 0. There we see our first doubling. And then the 4 goes in, I get that 16, -8, -6. So from this, I can now graph what the f of x function would look like, just the f of x. So I'm going to pause the video and show you what that looks like. So there is my f of x graph. Now to draw the g of x graph, let's think about what that's really telling me. The g of x graph is saying, take all the f of x values from up above here. It says take all these f of x values and subtract 7. So really, all I have to do is go into my table and say, subtract 7 from that value to get -13. Subtract 7 from that value to get -7, and -5, and -7, and -13. And so again, to draw my graph of the g of x function, I'm going to come off the chart by a little bit, I think, but I'm going to pause the video for a second and draw what that looks like. So there you have the g of x function. And it did come off the chart a little bit, but it basically would have the same opening. It is both opening downward, and what you'll notice is that we've had a vertical translation happen with the 7 units down. Okay, so up here it says take the f of x values and subtract 7. So we're saying this one is going to have the vertex at 2, which we should have noticed right here, and then we're dropping 7 units from that. So initially we saw this was going up 2 units from 0, 0 to get to this point. And then this one right here tells me to drop 7 to get to this point. So then it says to write an equation that's representing g in terms of x. So now without having the g being f of x minus 7. Well, think about it. If I just combine those two things, we know this from the function notation. If I was to take g of x and I substitute this thing right here, -1/2 x squared plus 2, in place of the f of x symbol, that is going to allow me to now finish this off. So that's the plugging in the f of x, and then we subtract 7. Now we know we can combine some like terms. We can only combine a few like terms. If I combine a couple of like terms, 5 minus 7 is negative 2. So that would be writing the equation of g in terms of x, not as the f of x. We would have g of x equals negative 0.5 x squared minus 2. Next, we want to talk about an important definition here for the zero of a function. So the zero of a function, this is actually another term that we've been using, just not this term. The zero of a function is an x value where the function's value, the f of x, is worth 0. So basically it is the x when y equals 0. So the zero of a function is an x-intercept. So when you think about it, the coordinates of an x-intercept are x comma 0. So the x value when the y is a 0 is called a zero of the function. So we've talked about this in the past. We've talked about how when we were doing roots, we found the solution to a quadratic. We talked about them as solutions. We're now going to see on a graph, you can see that root or solution also referred to as the zero or the x-intercept. And lastly, we want to talk about a real-life problem. So here we have the function f of t, negative 16t squared plus s sub 0, where we're representing the approximate height in feet of a falling object t seconds. So that's an important thing to note, that seconds is our t value after it is dropped from an initial height s sub 0. So that height is telling us how high up we let it go. The egg is dropped. So notice we're not throwing it. It is not going away from the building. It is just not going up in the air. It's just being let go straight down to the ground. Okay, from a height of 64 feet. How many seconds until it hits the ground? So a couple of things I want you to note here. So we're going to first make this graph. So thinking about our table, if we wanted to draw a graph with a table that was very accurate to this situation, we wouldn't show any negatives because I can't drop it seconds ago. It's going to be dropped from now and going forward. So our x is going to be our seconds, and the height, which is our feet, would be how high up off the ground we would be. So we're really only going to focus on quadrant 1. So let's make our table. We're going to look at a couple of things here. We're going to focus on not x, but a t, because that's what they gave us up in the directions, the variable t for our domain, and then the value of the function f of x. Now, they gave us the model f of t, so we want to make sure we know what we're really plugging in here. They told us that it was negative 16 t squared plus s sub 0. Well, we were told that we were dropping from an initial height of 64. So there's the actual function that we want to use. So let's go with 0. That's when I first let it go. That's how high up off the ground we are. If I plug in t, 0 squared is 0, times negative 16 is still 0. That function value is 64 feet high. After a second goes by, now I would do t squared, 1 squared is 1, times negative 16 is negative 16, plus 64 is now 48. Then what's it look like at 2? If I plug in 2, 2 squared is 4, times negative 16 is negative 64, and plus 64 is 0. So there's no point in going on beyond that, because really what that is telling me is a very important thing. That is actually telling me that in 2 seconds we have hit the ground, because the value of that f of t is how far in height we are after a certain number of seconds. So let's think about what we want to do for our graph. So I'm using a scale of 8s. I see my table looks like 8s would be a good number to use. I'm going to use a scale of 8s. Now my time, or my t, I'm going to stretch those out a little bit. I'm going to basically go by half seconds, because I think it'll be a little bit better than just having it all jammed at the left side, right side of the graph. So to start plotting my points, sometimes they're not going to come out nice and perfectly. This one actually works out well. 0, 64, 1, 48, 2, 0. So what you're going to see here with a nice smooth curve is there is the graph. Now, we weren't asked to do this. If we were asked to just graph like we were, we would also have seen that this was going to start curving right back down and land over here on this side. Okay, but what we were looking at is just this positive piece because we're in quadrant 1. Okay, so to answer the question, it is right here at 0 height. It took 2 seconds. So again, we just want to make sure we answer the question. 2 seconds to reach the ground. And for the last question, suppose the initial height is adjusted by k feet. What I also want us to notice in this graph, so we talked about dropping the egg. The egg would have dropped straight down. I also just want you to notice that that's not what the graph looks like it's doing. Don't be confused with this being what we are doing and the dropping looking like that. We're not throwing the thing away from the wall. This is showing us over time how close it is to the ground as it goes. We all hopefully realize that over here we are dropping it straight down. So just don't get confused on that, especially when you see any of these word problems. That arc going away is talking about where it is in time, not what it is physically doing by dropping straight to the ground. Last one. So here we are looking at, suppose that our initial height, so that initial height is being adjusted by k feet. How will this affect my answer? Well, we said where it is right now, at 64 feet, it is going to take 2 seconds. So a couple of things. What's going to happen then if the k is less than 0? So what we've said is that plus number, in this case, if it was a negative, it's going to drop, which means it's going to be less than 64 feet. Now remember, we're talking about exponential things happening, so I can't just say, well, if it drops 3 feet, it's going to happen this much faster. We got to run it through the numbers. But if it is a k value that is less than 0, it is going to take less than 2 seconds, which hopefully makes some sense because I'm closer to the ground. If the k value is greater than 0, now I'm higher than 64 feet, it's going to be more than 2 seconds. And then depending on how much higher it is, how much lower it is, we certainly can figure out specifically how many seconds and what the difference is. But just in general, if that k value is positive, that means it's up higher, which means it's going to take longer than 2 seconds. If it's less than 0, it's going to take less than 2 seconds because you're closer to the ground to start. So hopefully we are good with this. Keep making those tables to really see how this is working, but keep noticing what is happening with this vertical translation. We saw the same thing happening with our absolute values back in the past, that if you see something that is a plus c at the value at the back, we are raising our vertex up. If it is a minus number for the k value or the c value, you are dropping your vertex. So please let me know if you have any questions, and hopefully this will go pretty well, and we'll see you soon.